These organic compounds will be containing carbon and hydrogen, and it's not necessary that it will be carbon and hydrogen always. It can be other elements as well. So in 1828, Frederick Wöhler, he was the first one to prepare an organic compound in the laboratory from an inorganic compound. Electron charge cloud of pi bond is located above and below the plane, and they provide the most reactive centers in molecules containing multiple bonds. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So today we are back with Unit 8 of your syllabus, that is Organic Chemistry, some basic principles and techniques. So we are beginning with Organic Chemistry. So in today's session, we are going to study about, the introduction of organic compounds. What is organic compounds? What is organic chemistry? What are we going to study about it? All of that. And then tetravalence of carbon and the shape of organic compounds. Then hybridization and bond characteristics and the structural representation of organic compounds. So before understanding each of these topics, let us understand, or it is necessary to understand, what we are going to study in organic chemistry. Right. So organic chemistry or organic compounds, as the name suggests, we are going to study about organic compounds. That is organism. The name organic symbolizes organisms. That means that these organic compounds can be obtained from the plants and animals and natural substances. Right. So let's see the definition. Organic chemistry is a study of structure, properties, composition, reactions and preparation of carbon containing compounds. So organic compounds are compounds which contains carbon. So the main focus or the main element in organic compounds is carbon. So are all carbon containing compounds organic compounds? Not necessary, right? Yes, most organic compounds contain carbon and hydrogen, but they may also include many other elements. So these organic compounds will be containing carbon and hydrogen, and it's not necessary that it will be carbon and hydrogen always. It can be other elements as well. Carbon, hydrogen plus other elements will be present, right? So organic chemistry, how can we define it? It is the branch of chemistry that deals with hydrocarbons and their derivatives. So in general, we can say organic chemistry is the branch of chemistry which deals with the study of hydrocarbons and its derivatives. What does that mean? Hydrocarbon means the compounds which contains hydrogen and carbon. Hydrocarbon, that means hydrogen and carbon, and their derivatives. And their derivative means carbon and hydrogen containing compounds, plus there can be other elements as well. So in general, we can say organic chemistry is about those compounds, that is the hydrocarbons and their derivatives, right? Now hydrocarbons are the major class of organic compounds and they contain only carbon and hydrogen, as the name suggests, hydrocarbons, right? So it contains carbon and hydrogen. All other organic compounds are formed by replacing one or more hydrogen atoms of hydrocarbons by other atoms or groups. So they are called as hydrocarbon derivatives. As I said, instead of hydrogen, there will be some other element which is being replaced. That is how you get the hydrocarbon derivatives. So in hydrocarbons means only carbon and hydrogen will be there, but there can be other elements as well by the replacement of a hydrogen atom or a group of other atoms. Clear? Right. Now all carbon compounds present in plants, animals are organic compounds. So carbohydrates, proteins, vitamins, nucleic acids, amino acids, fats, oil, all these are examples of organic compounds. So in our human body itself, this proteins, DNA, amino acids, all of this constitute the organic compounds. So I hope it is clear for you that studying about organic compounds, and that is the organic chemistry, is really important for you. So this chapter will function as a base for your next year as well. That is organic chemistry. So I hope you are clear with organic chemistry and what are organic compounds. Right. So now let's have a understanding about the history of organic compounds. So as I said, organic compounds, it is obtained from natural substances, from plants and animals. Organic compounds can be obtained. So earlier it was believed that this organic compounds can only be obtained from the nature and it cannot be prepared in the lab. Okay, yes. So in ancient times, it was believed that a vital force, okay, there is some force is necessary for the production of organic compounds. Okay, there is something which is called as a vital force which forms this organic compounds, and that you can get to see, or this organic compounds can be obtained only from the natural substances like plants and animals, which is formed by something which was termed as vital force. So that means that those times, in ancient times, they believed that, the scientists believed that the organic compounds cannot be prepared. Right. So in 1828, Frederick Wöhler, okay, he was the first one to prepare an organic compound in the laboratory from an inorganic compound. So what did he do? From an inorganic compound, he was able to prepare an organic compound. Okay, so that was the first ever organic compound made. Right. So he prepared urea in the laboratory by heating ammonium cyanate, and it was the first organic compound prepared in the laboratory. So till then, scientists believed that it cannot be prepared, but he was the first one who prepared it. Right. So from ammonium cyanate, NH4CNO, that is ammonium cyanate, when it is heated, urea was obtained. Yes. So urea is an organic compound and your ammonium cyanate, it is an inorganic compound. So what did he do? From an inorganic compound, he prepared an organic compound. So the first ever organic compound is urea. Right. So then another scientist, Cole, he synthesized acetic acid, and Berthelot, he synthesized methane in the laboratory. Then afterwards, many other organic compounds were discovered. That is, many other organic compounds were able to be prepared in the lab. Right. And nowadays, about 95% of organic compounds are synthesized in the laboratory itself. Okay. So this was a history about the organic chemistry. Right. So now moving on to the next topic, that is tetravalency and catenation property of carbon. Okay. So as we studied now, it is the study about hydrocarbons and their derivatives. Right. So carbon is of utmost importance in organic chemistry. So before studying about the properties and naming of the organic compounds, we need to be clear about carbon and its properties. Right. So carbon is a unique element and it can form large number of compounds due to the following reasons. So as it is able to form these many compounds with each other and with other elements, this carbon is of utmost importance. Right. So the first property is tetravalency of carbon. Tetravalency of carbon. That means carbon is having a valency 4. Right. So what is the electronic configuration of carbon? It is 1s2, 2s2 and 2p2. Right. In the valence shell, how many electrons are there? Valence shell, 4 electrons are there. Right. So always the valency of the carbon is 4. So if the valency of carbon is 4, that means how many bonds carbon can form? Yes, carbon can form 4 bonds with other elements. Right. So in all of its compounds, the valency of carbon is 4. And carbon has 4 electrons in its valence shell and requires 4 more electrons to complete the octet. So it attains the octet configuration by forming 4 covalent bonds. So what, as I said, what is happening with carbon? Carbon is having 4 electrons in its outermost shell. So what does it do? Either it can lose the 4 electrons or it can gain 4 more electrons and attain its octet. So what carbon does it? Carbon forms bonds with other elements and they share the electrons with each other. Carbon shares these 4 electrons with other elements and completes its octet. So what is happening there? Covalent bonds are formed, right? So carbon forms 4 covalent bonds. Clear? Right. Now, ability to form single and multiple bonds. Now, carbon can form single and multiple bonds. Multiple bonds mean double or triple bonds, right? With itself and also with other elements. So, carbon can form single bonds with itself, double bonds with itself, also triple bonds with itself, and not with itself, with other elements also it can form double, single or triple bonds, right? Yes, now oxygen, nitrogen, etc. also it can form bond with, and this is possible by sp3, sp2 and sp hybridization. So in detail about hybridization we have studied in chemical bonding and molecular structure chapter. Yes, so now the next property is catenation. Now what is catenation? Carbon shows catenation. It is the self-linking property of an element to form long chains and ring. So what happens is, as we said, carbon can form bonds with carbon itself. So it binds with so many number of carbons, and that is the self-linking property of an element. That is, carbon links with itself. So it can form a big molecule, or else a long chains and rings can be formed. So that property is called as catenation. I hope you are familiar with the allotrope Buckminster fullerene. It is formed by a number of carbon atoms being joined with each other. So that is because of the catenation property of carbon. Now the next one is isomerism. Yes, isomerism. Carbon compounds can show isomerism. It is a phenomenon in which compounds having same molecular formula but different structural formula. Okay, so they will be having, that is, two different organic compounds. They will be having the same molecular formula. Their molecular formula will be same, but how they are present in the space, that is, their structural formula will be different. So carbon has that property also. So because of all these properties, carbon will be able to form a variety of compounds with other elements as well as itself. Right. Now coming on to the shapes of carbon containing compounds. So hybridization influences the bond length and bond enthalpy of the organic compounds. So hybridization is already familiar for you. So yes, what you have to remember, if it is sp3 hybridized carbon atom, yes, then they will have a tetrahedral shape. Okay, if the carbon is sp2 hybridized, the shape will be trigonal planar. If the carbon is sp hybridized, the shape will be linear. So what was hybridization? It was the intermixing of atomic orbitals of almost similar energy, right? So what happens if two atomic orbitals are combining, two hybrid orbitals are formed, and those hybrid orbitals will undergo the bond formation, right? So I hope you are able to recall about sp3, sp2 and sp hybridization, and these will be the shapes corresponding to them, right? Now coming on to the characteristic features of pi bond. So even this we have studied already, that is sigma and pi bond. Now how is sigma bond formed? Sigma bond is formed by the head-on overlapping of atomic orbitals, right? And now how is pi bond formed? It is formed by the sideways of overlapping, right? So let's assume this is one p orbital and this is another p orbital. Yes, how do they overlap? Yes, they overlap like this. If they do overlap like this, that is sideways overlapping. It is called as pi bond. Yes, sideways overlapping of the orbitals is called as pi bond. That is how pi bond is formed. Now, if it was like this, now here sigma bond is formed, right? Okay. Now the axes remain parallel and perpendicular to the internuclear axis. That means the axis of these two orbitals will be parallel to each other and it will be perpendicular to the internuclear axis. The internuclear axis is here. Yes, but the axis of the orbital is in this direction. So it is perpendicular to each other. And then free rotation about pi bond is restricted. Okay, so that means if there is a carbon-carbon double bond or carbon-carbon triple bond, yes, the rotation about this double bond or triple bond will be more restricted. That means it is very difficult for the rotation of the molecules. But in single bond, as there is no pi bond, yes, always wherever there is single bond, it is sigma bond, right? When double bond comes, it will be pi bond also present there. So single bonds doesn't have this problem. Free rotation is possible, but double and triple bonds cannot have free rotation possible because of the pi bond, right? Now electron charge cloud of pi bond is located above and below the plane, and they provide the most reactive centers in molecules containing multiple bonds. So this multiple bond containing compounds will be the most reactive. Okay, so I hope that is also clear. So now let's take these two organic compounds and let's calculate the number of sigma and pi bonds in this. How many sigma and pi bonds are present in each of the following molecules? So let's begin with the first compound, that is CH triple bond C, CH double bond CH, CH3. Okay, Yes, so wherever single bond you are able to see, that is sigma bonds, right? And double or triple bonds will be indicating the pi bonds, right? So let's calculate the sigma bonds first. Okay, we have to calculate the number of sigma and pi bonds, right? So the sigma bonds between carbon and carbon atoms we are going to see first. Okay, so there is a triple bond here between carbon and carbon. So there is a triple bond means, yes, one will be sigma and the other two will be pi, right? So one will be sigma bond and the other two are pi bonds. So in this case, one is there. Okay, now here one is sigma and one is pi, right? So that is also counted as one sigma bond. So in here one, here two. See, here one sigma bond is here. Here one sigma bond, here one sigma and pi is there, right? So one more sigma, here one more sigma. So a total of 4 sigma bonds, right? Between carbon and carbon. Now we are going to see the sigma bonds between carbon and hydrogen. Okay, so here one is there, here one, here, here, here and here. Okay, so 1, 2, 3, 4, 5, 6. A total of 6 sigma bonds are there between carbon and hydrogen. Okay, so a total of 10 sigma bonds are present, right? Now moving on to the next one, that is pi bonds between carbon and carbon. How many pi bonds are present between carbon and carbon? Double bonds, let's see. Okay, so there is one triple bond here, okay, and there is a double bond here. Double bond here means one is sigma bond and one is pi bond, right? So there is one pi bond there. And there is another one, that is in the triple bond. How many pi bonds will be there? 1 sigma and 2 pi bonds. So a total of 3 pi bonds. Okay. So a total of 10 sigma bonds and total of 3 pi bonds in the first compound. Now moving on to the second one, that is CH2 double bond C double bond CH CH3. Okay, again let's calculate the sigma bonds between carbon and carbon first. Here it is double bond, so 1 sigma and 1 pi. Here 1 sigma and 1 pi. Here a sigma, here a sigma. So 1, 2, 3, 4. Right? Now between carbon and hydrogen, how many sigma bonds are there? This is 1, this is 2, this is 3, 4, 5, 6. Again it is 6. So a total of 10 sigma bonds are here. Right? Now moving on to the next one, that is how many pi bonds are there? Only double bonds are here, no triple bonds. Right? So pi bonds between this, here 1 pi bond, here 1 pi bond. So that means 2 pi bonds are there. Right? So a total of, yes, 2. So 10 sigma and 2 pi bonds. Yes? So I hope it is clear. Right? So now moving on to the next part, that is structural representation of organic compounds. How we are going to represent the organic compounds, we are going to see. There are various methods in which we can represent this. So the first one is Lewis dot structure. Right. So the first one is Lewis dot structure. In Lewis dot structure, yes, we have already studied this in chemical bonding and molecular structure. Right. So how to represent the Lewis dot structure. Then comes complete structural formula, condensed structural formula, bond line structural formula and 3D representation. So as this is already known for you, I am not going into the details of that. Right. So the first one is complete structural formula. Right. So here all the bonds between the atoms are denoted by dashes. That means the bond. How do you represent the bond? With a line, right? A single dash represents a single bond. Yes, if it is just one line or one dash, it is single bond, right? Yes, and if it is two dashes, it's double bond, and if it is 3 dashes, it is triple bond. Right? Yes, so that is how you can write the complete structural formula. How to write the complete structural formula? All the bonds between the carbon and carbon, carbon and hydrogen, all the bonds will be represented by the dashes. And you have to see whether it is single, double or triple. Based on that, that many number of dashes you have to put. Right? So, let's take the example of C2H6. What is C2H6? It is ethane, right? C2H6. So, how do you represent the Lewis dot structure for that? You're already familiar with it, right? So, carbon atom, for carbon atom, what is the number of valence electrons? It is 4, right? So, that many number of dots, you will put it around the carbon atom. That is Lewis dot structure. So, for this carbon atom, there is 1, 2, 3 and 4. Right? Yes, 4 valence electron, and each hydrogen atom, it will contribute 1 electron, because how many electrons are there in valence electron of hydrogen? It is 1. right? Now this hydrogen and carbon will share the electrons between each other and both of them will complete its octet. Hydrogen complete its duplet and carbon will complete its octet. Okay, so this way both of them will attain its octet. So this is how you represent the Lewis dot structure. Now coming on to the complete structural formula of ethane. How do you write it? You can't write it like this. All the bonds you have to represent. So this electron, right, there is, let's take this one part. Yes, there is one electron which is being present in the valence electron of the carbon and one in the hydrogen. Right. So these two electrons will be shared between each other. Right. So now these two electrons being shared is represented by a dash. Now that is a bond. Okay. So that is what is shown here. So how do you write? C, H, H, H. And another between the carbon and carbon, one bond, one single bond, and the other three hydrogen, which using the dashes we represent. Now coming on to ethene. Ethene is an alkene. Yes, alkene means there will be double bond. Okay, so how do you represent? The carbon and carbon, between them there will be a double bond and the other hydrogen atoms will be represented by a single bond. Now coming on to ethyne, how do you represent it? It will be C triple bond and then hydrogen on the either side. So all the bonds between the carbon and hydrogen have to be represented. So that is complete structural formula. Now the next one is condensed structural formula. So here the carbon-hydrogen bonds or all the bonds are omitted except the multiple bonds. So it is a simplified representation of an organic compound. So we studied complete structural formula. Now we can simplify it and write, instead of mentioning all the bonds, we can simplify it and write. That is called as condensed structural formula. So ethane, how you can write it? Ethane, how did we represent it here? It was CH3 and CH3, right? Here all the bonds were shown. So how you can condense it and write? I can write this part as CH3 and this part as CH3. So CH3, CH3, I can write it like this, right? So that is what is shown here, CH3, CH3. Now how can propane be written? CH3, CH2, CH3. Same way, butane and ethene, all of this can be represented like that. See, ethene also, let's take the example. It is CH2 double bond CH2. Right. So how can I write the condensed formula? Instead of writing all the bonds between them, I can just write CH2 double bond CH2. So this double bond we can't omit. Double and triple bonds we have to write. Here it can be drawn, or if even you don't write the single bond also, it's not a problem. But double and triple bonds have to be represented. Clear? Now coming on to the other one, that is butane. It can be also written as CH3, CH2 twice CH3. Okay, it is CH3, CH2, CH2, CH3. This is butane, right? So there are two CH2 here. Instead of writing this much, I can just write it as CH3, CH2 twice and CH3. Even that way it can be written. So this is the condensed structural formula, right? Moving on to the next one, that is bond line representation. So it is the simplest form of representation of an organic compound. Here carbon and hydrogen atoms are not shown and the lines represents the carbon-carbon bonds are drawn in a zigzag fashion. So till here we studied complete and condensed structural formula. Now in this case, that is bond line structural representation, there are no carbon and hydrogen atoms written there. Just the bonds between carbon and carbon will be represented. Okay, we are not writing the carbon and hydrogen here, they're just the bonds between them. Okay, and that will be represented in a zigzag fashion. The only atoms specifically written are oxygen, chlorine, nitrogen, etc. If there is any other element other than carbon and hydrogen, they will be represented. Okay, now the free terminals denote CH3, that is methyl. CH4 is methane, CH3 is methyl. Okay, so let's take the first example, that is propane. Propane, what it is? CH3, CH2, CH3. So how can you represent the bond line representation? It's just by a zigzag line, right? So this is how you represent. So this part, as you can see, here one carbon atom is here one carbon and here one carbon. Okay, so as written here, the free terminals denote CH3. So this carbon atom, it has one bond with this carbon atom. So how many bonds can carbon form? Only 4, right? So one is already here. So how many will be there? It will be CH3 here, right? Now this carbon, one bond here. So now how many bonds it can form with hydrogen? It will be 2. So that is CH2 there. And here again it will be CH3. So instead of writing all CH3 and CH2, you can just write it like that. Now moving on to next one, butane. CH3, CH2, CH2, CH3. So CH3 will be here, then CH2 here, CH2 here, CH3 here. Both of these are free terminals that represent CH3 and the in-between ones will represent the CH2. Right. Now propanol. There is a functional group also here. Okay, not just carbon and hydrogen, oxygen is also here. Now what do I do? Okay, CH3, C double bond O, CH3. Okay, so one CH3 is here and one CH3 is here. So in between there is a carbon atom which is having a double bond oxygen atom. With oxygen atom it is forming a double bond. Okay, so that I do have to represent it like this. Okay. Right? So the free terminals represent CH3 and the middle carbon atom is having a double bond with oxygen which has to be represented. Now coming on to a cyclic compound. As you can see, CH2, CH2, CH2. They are in a cyclic form. That is a closed chain it is. These all are examples of open chain which we will be studying in detail in the classification of organic compounds. So yes, you can see it will be represented with this way. Are there any free terminals there? No, right? So there won't be any CH3 there. It is all CH2. Okay. I hope it is clear, bond line representation. Now moving on to the last representation, that is 3D representation. Okay. How you can represent the molecules that are 3D on a paper or a board if you have to represent it. How you can represent it? Okay. The 3D structure, how you can represent it on a paper, we are going to see. Okay. So here the structure of an organic molecule can be represented using solid and dashed wedges. Okay. There are solid wedges and dashed wedges. We have studied the normal dash, right, which represents the bond. Okay, so those bonds represents the bonds which are present in the plane. Now solid and dashed wedges are also used. For what? We'll see. Okay, solid wedge is used to indicate a bond projecting out of the plane of paper. That means it is towards the observer. Okay, and the dashed wedge indicates the bond projecting out of the plane of the paper and away from the observer. Okay, so the broad end of the wedge is always towards the observer and the bonds lies in plane of the paper are depicted by normal line. So the normal line depicts the bonds which are present in the plane. Okay, and the solid wedge represents the bonds which is towards the observer. Okay, which is towards the observer or which is out of that plane. Okay, right? And the dashed wedge represents those bonds which is away from the observer. That is means on the other side. That is away from the observer. Okay, so let's take this example, that is CH4, methane. As you can see, this bond and this bond, they are normal bonds, normal dash. So both of these bonds are present in the plane of the paper. Okay, in the plane of the paper that you are writing. Let's see, both of these are on the same plane. Now this is a dashed wedge. Now this dashed wedge represents, that means this carbon and hydrogen bond is in the 3D structure. It is away from the observer or else it is towards the paper. Okay, that is bond away from the observer. Now what about the solid wedge? And this solid wedge will be towards the observer. That is how you represent it. Now when drawing the solid wedge, the broad end of the wedge, that is, if this is the solid wedge, this broad end should be always towards the observer and you should not be writing it like this. This is not correct. This is the correct one. That should be towards the observer. Okay, so I hope it is also clear. So I hope different structural representations is clear for you. Complete, condensed, bond line and the 3D representation. Okay, so now let's do a quick recap of it. That is, expand each of the following condensed formulas into their complete structural formulas. The condensed formulas are given. You have to write the complete structural formula. That means all the hydrogen, carbon, carbon bonds, all this have to be represented. So the first one is CH3. So I write CH3. Okay, CH3, CH, all the bonds. Then CH2. So that means carbon and then 2 hydrogen. Now there is CO. Now that is a functional group. Okay, C, then double bond O with this. Okay, CO and CH2. Again there is a CH2 and then last there is again a CH3. Okay, yes, in all these cases, in all the carbon atoms also you can observe that they are forming only 4 bonds, right? They are having tetravalency, means it can only form 4 bonds. Okay, in this carbon atom 1, 2, 3, 4, in this one 1, 2, 3, 4, in this carbon atom 1, 2, it is forming a double bond with oxygen, right? So already 2 of its valency is gone. Now 1 and 2 here, right? Now this carbon atom 1, 2, 3, 4, this carbon atom 1, 2, 3, 4, right? Now moving on to the next one, that is CH3. Again, complete structural formula, CH3. Now, CH is there. So, CH. Now, a double bond is there. So, exactly I represent the same double bond. Then I write the carbon. Now, after carbon, that is CH3, CH double bond. Again, there is a CH. Now, there is CH2 thrice. That means there are 3 CH2s. Right. After this, there is 1 CH2, 2 CH2, and the third CH2. I hope it is clear. So, this much part, that is these 3 CH2s were represented inside this bracket as CH2 thrice. And the last one is CH3. Okay. Yes. I hope it is clear. Yes. Okay. So, in the next session, we will be studying about the classification of organic compounds. As I said, the classification of organic compounds, we will be studying homologous series and the nomenclature of organic compounds. We will start with the nomenclature of organic compounds as well. So, I hope what and all we have discussed in this session is clear for you. So, that's all for today. Thank you.